There are several basic forms of integrals of trigonometric functions that will hopefully be familiar to us. For example, if we were to consider the integral of the sine of x with respect to x, this is simply asking for the antiderivative of the sine of x, which would be the negative cosine of x plus a constant. Whereas the integral of the cosine of x, once again, is simply asking for the antiderivative of the cosine of x, which would be quite straightforward. Sine of x plus a constant. Additionally, if we had other common derivatives of trigonometric functions like the secant squared of x or the negative cosecant squared of x, those would also be very straightforward to antidifferentiate. However, there are four other trigonometric functions that we are going to integrate. One of them is the tangent of x. Now, there are actually two different ways to come up with this integral. One of which is to apply a quotient identity to the tangent of x and call this the sine of x over the cosine of x dx. I mentioned in the previous video that what we're looking for when we're applying the substitution rule is the presence of an inside function as well as the derivative of the inside function. You'll notice that sine of x is a form of the derivative of the cosine of x. So what I'm going to do is let u be equal to the cosine of x. Then for the differential substitution, that means that du is going to be the negative sine of x times dx. Now the reason that we can't go the other way around is because we would have a cosine of x times dx. This is dx divided by cosine of x. That's why that one wouldn't work out. However, we need to contend with this minus sign, so I am going to point out the fact that sine of x times dx would be equal to negative du. So when we perform our substitution, we're going to wind up with an extra negative sign in here. First off, I'm going to write this as 1 over the cosine of x times the sine of x times dx so that I can make all of my substitutions appropriately. This is now the integral of 1 over u times negative du. The negative is a constant multiple and can be pulled out. Then we're finding the antiderivative of 1 over u with respect to u. This would be the natural log of the absolute value of u plus a constant. Substituting back will be the negative natural log of the absolute value of the cosine of x plus a constant. This is a common one that shows up quite frequently in Calc 2. You'll want to have this one memorized and ready to go. There is, however, a secret second way to do this problem that also makes use of a u substitution. Now, this is going to make absolutely no sense as to why I decide to do this, other than, well, it works. What I'm going to do is turn this into a fraction, and I am going to multiply top and bottom of the fraction by the secant of x. Why on earth would I do that? Well, because we're about to do something that works. I would like to let u be equal to the secant of x. Then for the differential substitution, du would be the derivative of the secant of x. That is, the secant of x times the tangent of x times dx. And by some miracle, we have a secant of x times the tangent of x times dx in the numerator, and a secant for the substitution for the denominator. What we have done is created the substitution 1 over u times du. Well, that's exactly the same as what we integrated back here, and we got the natural log of the absolute value of that thing. So this will be the natural log of the absolute value of u plus a constant, which is equal to the natural log of the secant of x. Natural log of the absolute value of the secant of x plus a constant. I would like to point out, though, that the secant of x is the reciprocal of the cosine of x. And if I were to take the reciprocal of the secant of x, I would wind up with a power of negative 1. And according to logarithms, you're allowed to make powers into coefficients. So it works out either way. Using a very similar substitution, the integral of the cotangent of x times dx, we can once again use a quotient identity to turn that into the cosine of x over the sine of x times dx. and use the following substitution. Let u be equal to the sine of x. Then for the differential substitution, du would be equal to the derivative of the sine of x, which is the cosine of x times dx. Now that means I can take this cosine of x and this dx and make a substitution on those and turn this once again into 1 over u times du. We already know from the previous result that that will be the natural log of the absolute value of whatever we substituted. So natural log of the sine of x, natural log of the absolute value of the sine of x plus a constant. Now the reason that I brought up this technique for the tangent of x is because for the integral of the secant and the cosecant, we do something incredibly similar, which is to kind of pull something out of thin air and make it work. So for the integral of the secant of x dx, once again I'm going to turn this into a nice big fraction. And the way that I'm going to do so is by multiplying by this thing that seemingly comes out of nowhere, and yet it's going to work out just so beautifully. I'm going to multiply top and bottom by the secant of x plus the tangent of x. By doing that, the numerator gets the secant, that'll be the secant squared of x plus the secant of x times the tangent of x once we distribute. The denominator will be the secant of x plus the tangent of x. dx still goes at the end. Now with that in mind, the substitution I'm going to use is let u be equal to what we just created in the denominator. Secant of x plus tangent of x. Then for the differential substitution, du would be equal to the derivative of this. Derivative of secant of x is secant of x times tangent of x. And derivative of tangent of x is secant squared of x dx. By some miracle, this just happens to be what's in the numerator, just written in the opposite order. That means that if we make this substitution, this will once again turn into the integral of 1 over u times du, which from the last couple that we did, this is the natural log of the absolute value of the thing that we substituted, plus a constant. I tell my Calc 1 students, this one shows up all the time in Calc 2 and in Calc 3. Memorize this identity. It will serve you well. Now if we wanted to do something similar for the cosecant of x, it essentially works exactly the same way. Except instead of secant and tangent, I'll be using cosecant and cotangent. So cosecant of x plus cotangent of x over cosecant of x plus cotangent of x. Now distributing through the numerator is going to give me the cosecant squared of x plus cosecant of x times cotangent of x, all over cosecant of x plus cotangent of x dx. As I did on the previous 3 examples at this point, I am going to let u be equal to the bottom, and a miracle is going to happen up top. So cosecant of x plus cotangent of x, then du is going to be equal to the negative cosecant of x times cotangent of x minus the cosecant squared of x dx. That is, aside from the negative signs, exactly what we have in the numerator, which means that when I make a substitution on this, I will get 1 over u times negative du. We have already seen several times that that is simply going to turn into the negative natural log of the cosecant of x plus the cotangent of x plus a constant. Know these formulas well.